All right, let's talk about the stability of substituted alkenes, and we will begin with a topic called the heat of hydrogenation. So, for example, if we take a alkene and we add hydrogen with a platinum catalyst, what this does is it reduces the alkene to an alkane. So we can have C bonded to C, CH3, and you would have H's, H, H, and CH3. So it gives the saturation back to the unsaturated molecule. So the amount of heat required to hydrogenate a alkene can be measured. So the least stable alkene will have the most, and I can say the largest, negative heat of hydrogenation. Okay, so the converse is true for the most stable alkene. Will have the least, and I can say smallest, negative heat of hydrogenation. Okay, now your alkane, stability wise, is going to be more stable than the alkene. So during this reaction, energy is released, and the alkene that releases the least amount of energy is most stable. This is the take-home point. The alkene that releases the least amount of energy. Okay, so if we look at this energy schematic, and this is a transalkene, this is a cis alkene, and this terminal alkene here So when we hydrogenate each one of these molecules, we wind up with the product of an alkane. So any type of butene when you react it with hydrogen and a platinum catalyst, it will give you butane. So we can compare stability-wise via this reaction that the trans alkene loses the least amount of energy during this reaction of roughly 27.6 kilocalories per mole. And this terminal alkene loses the most amount of energy for that reaction. So we say that thermodynamically speaking, that trans alkene is more stable when you compare it to the cis and the terminal alkene. Now, what we can talk about now are levels of substitution. For an alkene. Okay? So when we talk about levels of substitution, let's take a look at this simple ethene molecule. So when we talk about something being substituted, just like with your alkanes, we're talking about some type of group, and preferably it would be an alkyl group. Some type of alkyl group taking the place of these hydrogens. So if I look at this ethene molecule, there are no substitutions. So another way of saying this is an unsubstituted alkene. All right. Now, if I take this same ethene and I put a hydrogen, 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 and say I substitute one of these hydrogens for an R group. And you know, your R groups can be methyl, ethyl, propyl, and so on. So if I substitute one hydrogen in ethene, this gives us a mono substituted alkene. Okay, so if I use this example here, if I say carbon, carbon, CH2CH3, H. This is an example of a monosubstituted alkene. Okay? If I did this, if I said this, CH3H, that is also an example of a monosubstituted alkene. So simply replacing one H on the ethane with an alkyl group gives me a monosubstituted alkene. Okay? So, guess what happens when we replace two groups? Any two groups. So if I say CH3 here, H, H, and I have CH2, CH3 here. This is an example of a disubstituted alkene. Okay, so that disubstitution can occur like that. So you would have, just say, an R group like this, like that. That would be representative of that. And we could also have another disubstitution that takes place on the same sp2 hybridized carbon. So we could have, let's say we wanted a CH3 here, a CH3 here, CHH. This also constitutes a disubstitution where your R groups are CH3s in that case. Okay? So you can see where we're going with this. If we had a trisubstitution, let's say a trisubstitution, so any R group that replaces 3 hydrogens on ethene, we would have a trisubstitution. So I could have a situation like this, C double bond C. I can put a CH3 here. Any R group is going to do. I can have a CH2, CH3. I can have a CH2, CH2, CH3. And I can have an H. So any R group would constitute a substitution. So I've substituted with, I can substitute with the same, or I can substitute with 3 different R groups. This is going to give me a trisubstitution. Okay? And the highest degree of substitution that you can have, you've probably guessed it, is a tetrasubstitution. So if I have carbon, carbon, and I replace all of my hydrogens on ethene with R groups, this is a tetra substitution. So an example of that would be carbon double bonded to carbon. I could have CH3, CH2, CH3, CH3, CH2, CH2, CH3. This constitutes a tetrasubstitution. Okay? So now we want to come into something that we're going to look at for elimination reactions. It has a special name called Zaitsev. CAITSEV' rule. So, in general, alkenes with more highly substituted double bonds are usually more stable. Okay, so when we get to elimination reactions, which is in this chapter, you will be able to go from a alcohol to a alkene, or you will be able to go from a alkyl halide to an alkene. You'll be eliminating a halogen and an adjacent hydrogen, producing an alkene. Zaitsev rule comes into play when we're looking at specific products. So another way of stating this, you can say that the most substituted product is usually more favored and stable. So what I mean by that is, if we have a tetra-substituted product, let's say we have C double bonded to C, and these R groups are alkyl groups, so it's going to be more stable than a tri-substituted. Which is going to be more stable than a disubstitution, which is going to be more stable than something that's just monosubstituted. Okay, so one particular objective in this course is to be able to recognize an alkene and its level of substitution. Okay, do not get degrees of unsaturations confused with level of substitution for an alkene. All right, so for example, if I draw this structure, I'm just drawing this off the top of my head. What level of substitution is this? Okay, so what you should be able to recognize is, all of this goes back to the things we did in chapter 1, being able to recognize the molecular formula, what group is what, and understanding that this is a carbon and that's a carbon, and this is an implied hydrogen. So if I circle my R groups, this is a what, CH3, this is a what, CH2, CH3, and this is a CH3. I can recognize that I have 3 levels of substitution. So this is tri-substituted. A tri-substituted alkene. Okay. Let's try this one. So I can ask the same question. What level of substitution is this alkene? So right off the top of your head, recognizing the structure of this, you should see, definitely from what we did in chapters 1 and 2, that this is a disubstituted alkene. This is a carbon, and you have what, 2 implied hydrogen here. So what are your 2 R groups that participate in substitution? Well, this is a CH3. And what group is this? This is a CH2, CH2, CH3. So this is a di-substituted. Okay, so we can do several of these and get the hang of it. So this should be very quick. If I have something like that, what level of substitution is this? So you should recognize that this is tetra substituted. So we have this R group, this R group, this R group, and that R group. Okay? So, definitely in this chapter, you have to understand Zaitsev rule and the level of substitutions within an alkene, because that will apply to what we do next when we start elimination reactions and trying to determine what's the most favorite product.